Assalamualaikum Prof. Jarot, Pak Rohadi.
Assalamualaikum Bapak Ibu sekalian. Pak Saiful.
Pak Jarot, Pak Saiful.
Ini udah siap ini, Pak Moderator.
Bisa loh, Pak. Jagoan-jagoan baru ini, Pak.
Ini yang lama cuma saya aja kan, jagoannya udah lapuk itu.
Oh, ada itunya ya, Pak, background-nya ya? Di mana background-nya ya?
Oh, sebentar, Pak. Saya kirim, Pak.
Dikirim jadi itu ya.
Nggih, siap, Pak. Jagoan-jagoan baru ini, Pak.
MC-nya Pak Adi di
Cuma saya aja kan, jagoannya.
MC-nya yang masih ngantuk, Pak.
Jam berapa Mas MY di sana?
Mau jam 3, Pak.
Oh, iya.
Tapi
Subuhnya jam berapa?
Bangun jam 1. Subuhnya jam 4.
Oh.
Ya. Jam 1 udah bangun ini. Ini masih
tahajud. Ya, banyak berdoa itu.
Sudah kami kirim Pak Rohadi. Saya WhatsApp itu. Oh, itu juga ada dia itu. Di chat juga ada.
Ya, banyak berdoa itu.
Terima kasih Mas MY.
Sudah kami kirim Pak Rohadi. Saya WhatsApp itu. Oh, itu juga ada dia itu. Di chat juga ada.
Terima kasih Mas MY.
Sudah kami kirim Pak Rohadi.
Zin, apa boleh dimulai atau mau nunggu mungkin jam 9.05 dan Radioactive.
Monggo dimulai Mas MY.
Oke. Mohon di-mute dulu ya teman-teman semuanya. Kita pakai bahasa Inggris ini karena pembicaranya dari Jepang. Terima kasih. Oke, bismillahirrahmanirrahim. Good morning, ladies and gentlemen. May I have your attention, please? Our session is about to begin. Thank you so much for preparing yourself to join our webinar sessions. Good morning, ladies and gentlemen. Our respectable the head of Research Organization for Nuclear Technology, Dr. Rohadi Awaludin, and the head of Research Center for Nuclear Fuel Cycle and Radioactive, Dr. Saiful. Our honorable speaker, Professor Satoru Nakashima from Hiroshima University, Japan, Professor Jarod Sulistyo Wisnubroto from our research center, Dr. Adi Raga Pratama from University of Indonesia, and then Mr. Susetio Haryo Putra from Universitas Gadjah Mada, and last but not the least, all the participants of this webinar. Before we start our session, we would like you to have a seat and sing the Indonesian national anthem.
Masih di mute, Mas MY.
Okay. Okay. Thank you so much. Thank you. Okay, Thank you so much for your attention. And now our next session will be the opening speech by our Head of Research Center for Nuclear Fuel Cycle and Radioactive Waste Technology, to Dr. Saiful Bahri. Time and screen are yours.
Thank you so much, Mas MY. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good evening, good night over there, Mas MY, in your places. First of all, I would like to welcome you all. Distinguished first, Dr. Rohadi Awaludin, Head of Nuclear Energy Research Organizations, and distinguished two speakers for today, Professor Jarod Sulistyo Wisnubroto from Center for Nuclear Fuel Cycle and Radioactive Waste Technology, and Professor Satoru Nakashima from Hiroshima University. And also we have two colleagues here from university, Dr. Adira Pratama from Universitas Indonesia, and Mr. Insinyur Sustio Haryo, MN from Gajah Mada University. And distinguished all participants today. First of all, I would like to welcome you all again, and it is my pleasure to be with you here today. All participants and guest speakers on our webinar today, the introduction to radioactive waste. And this webinar is part of the series of nuclear fuel cycle webinar. And this webinar aims to provide an insight and understanding for all of us what's the research in the field of nuclear cycle, especially for radioactive waste management today. And one of the implementation of both, either for energy or the non-energy, is how to manage the radioactive waste, which aim also to ensure the safety and of humans and also the environment. Therefore, ladies and gentlemen, by presenting the speakers who are expert in this field, also from overseas academics, we hope that we can expand our excellent research network and collaborations. And this is accordance with the BRIN directions. We know exactly how to creating a global standards, open and inclusive, also collaborative research ecosystems through development of advanced research and latest innovation in the science and technology. And we hope that it can help, this webinar can help us to formulating how the strategy to improve as well the human researchers capabilities in our research center and also in the BRINs, especially for the radioactive waste and fuel cycle technology. And the first speaker today, Professor Jarod Sulistyo Wisnubroto, he is the former chairman of Batan, if I'm not mistaken, 2012 until 2016, and he's also the expert in this field. And the second speaker, Professor Satoru Nakashima from Hiroshima University, he will give us the lecture about understanding the chemistry of lanthanide and actinide of high-level radioactive waste. This is the basic understanding, I think, for all of us to get a deeper understanding in the future what is the radioactive waste and what's the research in this field. And I believe that there's many benefits in these events, and we hope that we can obtain many knowledge as well. And maybe through this webinar also, new research idea can emerge, and we can build research collaborations among us. And again, before I close it, I do not forget to thank the committee to help this webinar, and also who prepare many things for this webinar as well. And I hope that we can enjoy this webinar. Thanks a lot. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you so much for our distinguished Dr. Saiful Bahri for the opening. And then for the next will be the opening remark by our Head of Research Organization for Nuclear Energy, to our distinguished Dr. Rohadi Awaludin. He will also officially open the session today. To Dr. Rohadi Awaludin, time and screen are yours.
Okay, thank you, Mas MY. Good morning, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Our respectable head of Center of Nuclear Cycle, Fuel Cycle, and Radioactive Waste Technology, our distinguished speakers, our honorable participants in this webinar. First of all, I would like to welcome.
Suaranya nggak kedengaran ya?
Nggak kedengaran, Pak?
Ya, kecil volumenya.
Kecil volumenya sepertinya, Pak. Iya.
Sebentar. Bagaimana sekarang? Tes.
Better, Pak.
Better, oke.
Ya.
Okay, I repeat. Good morning. Is it better, Pak Saiful?
Masih
kecil.
kecil, Pak.
lagi. Apa kecil lagi ya? Oke, now.
Coba dites lagi, Pak.
Tes. Bagaimana, Pak Saiful?
Masih kecil, Pak.
Masih kecil
Belum
ya?
ada perbaikan.
Udah perbaikan.
Kalau di kasus saya yang naikkan increase volumenya, Pak.
Oh gitu.
Iya.
Sebentar. Ini apa? Mikrofon. Tadi belum dicek dulu di awal ya. Bagaimana sekarang? Belum juga ya. Sebentar, Pak, saya ganti ini, pakai ini apa?
Oh, udah oke masuk ini. Oke. Ya.
It's better now, Pak Rodi.
Now better?
Yeah, it's better. Yeah, you can start.
Oke.
now.
Sorry for the inconvenience.
Masih kecil rupanya.
Kecil lagi. Sebentar.
Sorry for this inconvenience. We're still waiting for Dr. Hadi to get a better microphone so we can hear.
Now how about this one?
Oh,
I
lebih
think it's
kecil malah,
still
Pak.
same.
You change the microphone. I change the microphone. How about this one, Pak Saiful?
Lebih kecil malah, Pak.
Nah. Bagaimana sekarang?
Wah, mantap
Yeah,
yang ini, Pak.
It's
Okay.
much better.
Okay.
Okay, please.
Okay, I'm sorry for the inconvenience. Okay, good morning, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Our distinguished guest, Prof. Satoru Nakashima Sensei, and Prof. Jarod, and also the head of Center for Nuclear Fuel Cycle and Radioactive Waste. First of all, I would like to welcome all of you in this webinar, knowledge sharing webinar on introduction to radioactive waste management. Ladies and gentlemen, as all we know that Indonesia now have a target net zero emission in 2060. So I think we will use nuclear power in the near future. So we have to prepare, we have to increase our capacity in nuclear and radioactive waste. So I think it's very important for us today, our webinar today, to prepare our capacity in handling radioactive waste. And today we will discuss, we will have a lecture about lanthanide. And actually lanthanide chemistry is not only for radioactive waste, but our colleagues in radionuclear production, actually, they need also the capacity or the knowledge about lanthanide chemistry, because now many radionuclide is from lanthanide preparation and also in preparing the label compound. So it is important to have a basic knowledge about lanthanide chemistry. So I think it's very, very important our webinar today. And last not but least, I would like to thank all committee members of this webinar, and the member of Research Center for holding this webinar. I really hope that this webinar session can be continued more frequently. And my special thanks to our keynote speakers, Prof. Jarod Subroto and Prof. Nakashima Sensei, who are willing to share your experience with us today. And we are looking forward to enjoying your lecture. And hereby, I officially open this webinar event. And please enjoy the presentation and the discussion. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you so much for Dr. Rohadi Awaludin for opening this session. We would like also to invite you and all the participants to have a group of photo together. And this session will be led by Mr. Ade Saputra. So Mr. Ade Saputra, you can lead for this session. Time is yours.
Okay, first page. Next, second page. Next. Okay, thank you.
Okay, thanks so much for Mr. Ade Saputra. And now we are entering the main sessions. The main session will be led by our moderator, Dr. Triana Basuki. I will talk about his CV. So Dr. Triana Basuki was graduated his PhD from Hiroshima University in Japan. He has also published many publications in international reputable journals. And now he joined in the Research Center for Nuclear Fuel Cycle and Radioactive Waste Technology. He now also become a postdoctoral in the same university in Hiroshima University in Japan. So to Dr. Triana Basuki, time and screens are yours.
Thank you so much, Dr. Muhammad Yusuf, for a very kind introduction. Is my voice clear enough?
Yeah.
Dengaran, Pak.
Okay, thank you. So, ladies and gentlemen, as has been introduced before, I am Triana Basuki, the moderator of this session. I am very pleased to see all of you in this knowledge sharing webinar and welcome all of you again in this event. Today's knowledge sharing webinar is about introduction to radioactive waste management. So before the presentation begins, let me inform you how this session will be going on. At first, we will have a lecture or presentation, followed by the commentary session. So here we have two commentators from University of Gajah Mada University. And after that, we will open the QE session. So I hope your active participation during the QE session before we close this session. So in this knowledge sharing webinar, we are very fortunate to have two distinguished presenters or lecturers. First lecturer is Professor Jarod Wisnubroto from Indonesian National Research and Innovation Agency or BRIN. Good morning, Prof. Jarod. Thank you so much for joining with us.
Morning.
Yeah. So Prof. Jarod is going to talk about the current practices and research on radioactive waste management in Indonesia. So I think it is important for us, especially for young generation researcher or a newcomer researcher in this field, like me, especially. And the second presenter will be Professor Nakashima. He's from Hiroshima University. And unfortunately, he cannot join from the beginning of this webinar, so he will join with us around 10 a.m., because of he's now in the other meeting. He is going to talk about the basic knowledge of chemistry of lanthanide and actinide for basic understanding for high-level radioactive liquid waste using solvent extraction. As I do agree with the head of research organization for nuclear energy, that this knowledge is not only important for radioactive waste management, but for other processes. As I mentioned before, in this seminar or webinar, we will have two commentators. The first commentator is Dr. Adiraga Pratama from University of Indonesia. Good morning, Dr. Adiraga. I hope you have
morning.
joined with us. Oh, yeah, thank you.
Yeah.
Yes, thank you, Pak Adiraga. The second commentator will be Insinyur Susatyo Haryo, Master Engineering from Gajah Mada University. Good morning, Pak Susatyo.
Pak Triyono.
Yeah, thank you for joining with us. So, as usual, before we start the first lecture, I'm going to read the CV of the first lecturer. Although I'm quite sure that most of you have known him very well. So his name is Jarod Sulistyo Wisnubroto. He was born in Yogyakarta, 1st January 1963. I think your birthday is almost similar with Nakashima Sensei birthday, January 3rd. Yeah. Professor Jarod received his bachelor degree in nuclear engineering from Gajah Mada University, and he obtained his master degree and doctoral degree from Tokyo University, as you know, one of the best university in Japan. He has very outstanding working experience. He has served for some very important position in Indonesian National Nuclear Agency. His last position was the chairman of the agency from 2012 to 2018. I met him when he was the chairman, maybe in the 2017 in Tokyo, if you remember, Prof. Jarod. And he is very actively involving in very important society in Indonesia, such as the chairman of Advisory Board of Indonesian Village on Enterprises. He is a co-founder of Indonesia. He published some international publication on radioactive waste management and nuclear energy related topics. So to make it short, I hereby kindly invite Professor Jarod to deliver the lecture, maybe for about 40 minutes. Please, Professor Jarod, the time is yours.
Thank you, Mas Triyono Basuki. Good morning, Pak Rohadi, Pak Saiful Bahri, dear colleagues, everyone participant of this webinar. I'm very happy to be here to explain about the radioactive waste management in Indonesia, the current practices and also studies, the current studies and maybe future studies of the radioactive waste management. This topic is very important for us because when people or the public ask about the readiness of the Indonesian government or Indonesia on the nuclear energy program, they ask first about how about the radioactive waste? Can we manage that waste? Are we ready to manage that, or how we can treat the radioactive waste? So I will talk about first on the what is radioactive waste, and then what kind of radioactive waste and the practices that currently we do in BRIN, and also the challenges of the radioactive waste management in Indonesia. So this is the title that the committee asked me to give the talk today, this morning, current practices and studies of the radioactive waste management in Indonesia. So when we talk to the public, they sometimes mix between the radioactive waste and the garbage landfill, like TPA in Bantar Gebang or other locations. And I have to, we have a duty to explain to them, this is the waste. Just like pile of drums inside the buildings or in the water. So we can show to them, we manage in a good manner of the radioactive waste. And even our colleagues in BRIN or in Bataan, they were very active during the pandemic. Even some of us working from home, they were very hard working how to treat and to manage the incoming wastes during the 2020-2021 era. So we have to be proud of them. This is the pictures of the activities, the treatment of waste using the compactor and also the cementation of the waste. First, I want to talk about the definition of radioactive waste. This is very important. This is very important. Why we sometimes different with other countries when we talk about what is the radioactive waste. In our law, Act number 10, 1997, it is stated radioactive waste is radioactive substance and materials and equipment that have been exposed to radioactive substance or become radioactive because of the operation of nuclear installations that can no longer be used. So, what is the meaning of this definition? It means we have a limited definition of radioactive waste. It's coming from the nuclear installations, is radioactive waste. But outside that, for example, from the oil industry, we sometimes find the waste, radioactive waste, genome waste or non-waste. That is not radioactive waste. That's why in the past, when I was the director of Radioactive Technology Center, some people request us to collect and storage the genome waste. I said no, because that was not radioactive waste. I don't know in the future when we are in the process to revise this law, whether genome or norm will be defined as radioactive waste or not. But this is the current law of the radioactive waste definition. Then when we compare to the IAEA definition of radioactive waste, it's very flexible. Let's take a look and to read this definition. For legal and regulatory purposes, material for which no further use is foreseen that contains or is contaminated with radionuclides at activity concentration greater than clearance level as established by the regulatory body. It depends on the countries. It depends Indonesia, Malaysia, Singapore, or other countries to define what is the radioactive waste. And when we compare with Malaysian definition of radioactive waste, they are very flexible. Radioactive waste means any waste which contains all or parts of substance or item which, if it is not waste, is considered as a radioactive material or substance or item which has been contaminated during production and etc. So this is Malaysian definition, different with us in Indonesia. That's why BRIN or Batan in the past doesn't treat or manage the waste coming from the oil and gas industry, from tin minings and other non-nuclear facilities, because they are not radioactive waste in our definition. So we have to be understand first what is radioactive waste in our definition. And what is the policy of the radioactive waste management in Indonesia? First, we have a policy, a centralized management. A centralized management. It means the implementing body, or in Bahasa Indonesia, it is called the Badan Pelaksana, manage radioactive waste from all over Indonesia. What is the implementing body? Well, before 2021, Batan acted as the implementing body. And this is the third point of this slide is very controversial. Sometimes I have to discuss with several people, the lawyer. Is BRIN now the implementing body? Some people say yes, some people no. But anyway, there is no words or sentence that in the law, regulation, presidential decrees that stated BRIN is the implementing body. But anyway, we have to do to treat the manage the waste. So BRIN now act as the implementing body. This is the chart of the organization of the BRIN. Where is Batan right now? Ex-Batan, I mean. So there is Research Organization of Nuclear Energy. The head is Mr. Dr. Hadi. Then there are some part inside such as Deputy Research and Innovation Infrastructure. I have to use the pointer. Wait. So here there is one directorate, and here in Research Organization Nuclear Energy, and also in I think here, I don't know, and one polytechnic. So we are now the ex-Batan in BRIN in several parts of the organization of BRIN. In Research Organization of Nuclear Energy, in Deputy Development, not development, I think not development in here, sorry, maybe in here. Deputy Research and Innovation Policy, Deputy Research Innovation Infrastructure, including 3 research reactors and nuclear facilities, and the Polytechnic School of Nuclear Technology. So this is it, the ex-Batan inside BRIN. So when in the past we had center, Radioactive Waste Technology Center, the researchers now in these research organizations, but the facilities and the human resources, the radioactive waste treatment facility is inside the Directorate of Nuclear Facility Management. And when we talk about the policy of nuclear energy and other topics related to nuclear in this Directorate of Environment, Maritime, Natural Resources, and Nuclear Policy. And we have the School Polytechnic of Nuclear Technology. So this is us, the ex-Batan inside the BRIN, and I call it whether this is controversial or not. At the moment, the implementing body or implementing agency of nuclear is BRIN. So what is the current practices inside BRIN on the radioactive waste treatment? I think this is very classical technology. We conduct for the incoming waste from all over Indonesia, from the hospitals, from the industries, even from inside the reserve reactors, we conduct some treatment, delay and decay, because the radioactivity characteristics. So we just wait until the activity of the waste decaying, very effective for very short and half-life radionuclides, and change the composition, for example, including the incineration, the combustion to reduce the volume, flocculation, coagulation using the chemical treatment, and also we conduct the evaporate the waste. Here, oh sorry, combustion, and also the conditioning. Conditioning, it means just put the radioactive waste inside the container and pouring the cement or capsulation. This is what we do and what we are doing in BRIN on the radioactive waste, and we still going to use this technology for the near future. So this is the management of the radioactive waste. On the right side, we see how to manage the spent nuclear fuel. we receive the spent nuclear fuel from Serpong reserve reactors. That spent nuclear fuels goes to the interim storage for spent fuel, the ESSF, and we have two options: to re-export the spent fuel, or we just store them in the ESSF inside in the water and waiting for the disposal. This is the right side, the spent nuclear fuel management. But how about the waste coming from the research development organization, from the hospital and industry? We conduct several steps to, for example, to classify and to categorize the waste. And I forget, for the spent radiation sources, the waste generator, like hospital and industry, they have two options also, whether they want to re-export the sources or they move their sources to BRIN. Like spent nuclear fuel, for the spent radiation sources, so the generators, the hospital, the industry, or R&D organizations, they have two options: to re-export to the origin country, to the companies that they came from, or to BRIN. But mostly, the spent radiation source or disused sources, they move their sources to BRIN. Why? Because sometimes the contract to include the export is very expensive, or maybe the companies that the maker already no longer exists, or other reasons. Mostly the spent or disused sources goes to us, to BRIN. So this is the step from sorting and treatment. We conduct the treatment and some conditioning, and all of the waste is right now in the interim storage. So this is the interim storage. We have the interim storage for spent fuel and also the interim storage for radioactive waste. Then in the future, we would like to conduct the clearance. It means if the waste is below the clearance level, we cannot declare the material is not non-radioactive waste. We are still conducting the R&D on the disposal activities. I think some researchers in BRIN conducting the disposal activities, whether to find the technology like borehole, like near surface disposal, or the site, the location for this disposal facility. I think under Dr. Saiful Bahri, we conduct several activities on the R&D, like development of radioactive waste treatment technology, like here, and then development of storage technology, especially on the spent fuel, like how to find the technology, not only wet storage technology, but also the dry storage technology. And we also conducting, right now it's very active right now, some people inside BRIN on the decommissioning and decontamination, because some of our facilities already old. We have to find a way, if the management decide that we have to decommission some or a certain nuclear facility, we are ready to do that. And of course, the last one is development of design and safety technology for disposal of low, medium, and high level of radioactive waste. As I said before, we conduct the disposal research on the technology, not only on the technology, but also to find the site, the location. This is the radioactive waste classification. It's very similar with the IAEA recommendation of the classification. We have a government regulation number 61 in 2013. We classify into low-level waste, medium-level waste, and high-level waste. Anyway, some people ask me, what is the high-level waste, especially from the public? And I said, the high-level waste in us is defined as spent nuclear fuel. So because the policy of the Indonesia is open nuclear fuel cycle, so we define the spent nuclear fuel, whether coming from the reactor or coming from the nuclear power plant, is high-level waste. Later on, I will explain, is there a possibility that we conduct some study on the high-level waste, non-spent fuel? And I say, yes, it is possible, because we have a right to conduct that kind of activities. Where does radioactive waste come from in Indonesia? So first, coming from these reactors. From reactor 3 Mark II, Bandung, Kartini reactor, Yogyakarta, and the neighboring, we call it neighbors reactors in Serpong, the GA Sewabesi reactors. This is the main generators inside BRIN that generate radioactive waste. And they are collecting like spent nuclear fuel. At the moment, there are 287 bundles of spent nuclear fuel from Serpong research reactors and other solid waste, liquid waste, semi-liquid waste. And because the research reactor using the ion exchange, ion exchange to purify their water, their coolant system. So there are some liquid, semi-liquid waste that we have to manage. And the waste coming from the research reactors, they are transported to the installation of radioactive waste. And we conduct also the re-export, repatriation. The uranium that originated from United States, then to be fabricated by PT Unuki or PT Batam Teknologi in the past, the US government, they asked us whether we wanted to repatriate it or to re-export or repatriate. This is very voluntary, not the obligation. They just ask us. The US government asked us, do you want to repatriate the spent nuclear fuel that the uranium originated from the United States? If we say yes, then we conduct together for the repatriation. We conducted in 1999, 2004, and 2009. And even from the Jogja and Bandung research reactor repatriated in 1999 and also in 2004. And they still offered us, I think in 2015 or 16, whether we want to repatriate the spent fuel from Bandung research reactor. At that time, I was the chairman of Batan, and I said, no, we still can use it. Why? Because if we that Bandung research, the Bandung spent fuel research, Bandung spent nuclear fuel, spent fuel for the Bandung research reactor, but maybe it is useful as a fuel for the Kartini or Yogyakarta research reactor. I said, we have to prolong, we have to extend the operation of the Kartini reactor using the spent nuclear fuel from Bandung research reactor. That's why, I cannot say to reject, but I say no for the repatriation for 2016 or 17. This is a list of waste coming from the 3 Riset reactors. There are HEPA filters, liquid waste, and other solid waste. They just send it to us. To us, it means to the installation of radioactive waste inside BRIN. I cannot say us right now because now I work for the organization, Riset Organization of Nuclear Energy, but the radioactive waste treatment installation is different directorate. So how much from the hospitals and industries and other organizations in Indonesia? So BRIN collect the waste coming from non-destructive test activities, from irradiations, some irradiators, whether inside or outside BRIN, and from the use of measurement tools, the gauging, and from the hospitals, teletherapy, brachytherapy, gamma knife, and sterilization. That's why the groups of radioactive waste treatment installations is very busy collecting, managing the waste coming from all over Indonesia. And the Bapeten informed us there are 4,200 license holders for the use of ionizing radiation sources or the use of nuclear materials in Indonesia. But again, for the spent radiation sources, there are 2 options for the hospital or industries, whether they want to re-export to the origin company or country, or to send it to Serpong, to BRIN. But our experience shows that mostly they move their spent or disused sources to Serpong. The reasons, well, I explained before, because the contract is expensive, or maybe the company no longer exists, or other reasons. So this is the data inside BRIN right now. Maybe we have to update it, but at least this is data, the last year data. There are concrete cells, 19 concrete cells, with the volume 950 liters, and more than 100 concrete cell for the semi-liquid waste and others. And look in this number, maybe more than that. There are a lot of disused radioactive sources. Many. I think our colleagues, they are considering to reuse this DSRS or disused radioactive sources. It means maybe the industry or other entity or hospital want to use it again. It is possible. Or maybe in the future, we want to recycle it. But still, we have to develop our facility and technology. It needs the hot cells and other equipments and capabilities of our human resources. But this is very interesting. If we can reuse some of them or recycle some of these disused radioactive sources, so we can decrease the waste that in the interim storage. And this is very important things. When the waste generators move or transport their waste to BRIN, they have to pay the tariff. I don't want to show the, well, all of the tariffs. You can read the tariff in the government regulations number 8, 2019. But I just want to show you the tariff is very cheap. Very cheap. Look at this. Even we have a tariff in 2011, and then we have a tariff, we revised the tariff in 2019. We just increased a very small rupiah, even when comparing to the inflation and other things, because the government say it is prohibited to increase 50% or maybe, well, of course, 100%. And I want to say that this tariff means the government subsidized the management of radioactive waste. I remember when we first set up the tariff in 2001, long time ago, when I was young, with our colleagues, I think they are also here also, we include the calculation of the disposal. We include also the calculation of the long-term storage. But the tariff became very, very expensive. Then our boss at that time, our chairman and our deputy chairman of Badan said to us, no, it is not good for us because we have to consider the safety and security of the radiation materials. If we set up the tariff expensive, then the waste generator, maybe they just dump the waste everywhere to become open sources. So this is a kind of a philosophy, the tariff philosophy, that the government subsidizes the management of radioactive waste. And the government finances the long-term management and future disposal. But it will be different if we talk about waste coming from the nuclear power plant. We have to set up the tariff including decommissioning and also the disposal. We have to remember our waste in Indonesia mostly coming from the R&D and hospitals. And again, the government should protect the public and the environment from the risk of the radiations. That's why it's very, well, I say very cheap comparing to our calculation if we include the long-term storage and disposal facility that we have to construct. I think this is the picture shows, Triano, please say to me if I already more than 40 minutes. This is just a picture of the
5 minutes more.
Okay.
Yes.
Picture of the facilities.
You can speed up.
Okay, thank you. Evaporation, ion exchange facilities, and also the compactor, injection, HEPA filter, compactor, shredders, and also the cementations. And we have also the interim storage 1 and 2. I think the pictures is old pictures because the interim storage 1 and 2 is already almost full. So we are now requesting to the BRIN, chairman of BRIN for the new interim storage number 3. So we have to convince them that we need that interim storage number 3. This is the spent nuclear fuel. And the interim storage for that spent nuclear fuel inside the water. And our colleagues, one of our colleagues right now conducting the research on dry storage. This picture shows an industry use our disused radioactive sources. They are marine AMBE, it means the neutron sources. We promote that kind of activity because some of the disused radiation sources is still used. It can be used for the activities of research or maybe for the industries. And future studies. What is the future studies? Challenge for us: first, disposal. When, where, when, and what technology for the current and future radioactive waste. Because all of the waste is still inside the interim storage. And second, how about the non-thermal waste management? Although in the current regulation, it is not defined as radioactive waste, BRIN should be responsible for finding solution for non-thermal waste management. Even now we have also other term in bahasa Indonesia, materi ikutan radioaktif or something like that. And the third point is very important also, to decrease the waste inside our interim storage facility. Recycle development for disused radioactive sources. Well, it needs some additional facilities and capabilities of our human resources. Decommissioning of nuclear facilities, including technology development and cost estimation. Well, the cost is very expensive, of course, and we have to consider also where we want to put that kind of decommissioning waste inside BRIN, because the volume is huge. And we learn from the Batan Indah soil contamination. How about open sources and soil contamination? Fortunately, well, fortunately is not the correct proper word. The Batan Indah is just not far away from us, from Serpong facilities. But how about, for example, in Kalimantan, is accident or incident happen? So we have to consider that. And of course, because we are islands country, the challenge is also the transportation of radioactive waste from Papua, from Aceh, from Sulawesi, from Kalimantan. It's very challenging. There is possibility, well, not only accident, the criminal cases happens, or maybe the carrier reject to carry the radioactive waste. And of course, development of radioactive waste fund, because the current tariff is not enough. The current tariff for radioactive waste management is not enough. We have to convince the Ministry of Finance or Ministry of Development Planning, National Development Planning. This is very important, because if we don't have fund for radioactive waste management, how can we manage or to construct the disposal facility, for example? And of course, we are now, as the Pak Radi said, in the program net zero emission, we have to be prepared. Management of radioactive waste generated from the nuclear power plants. The nuclear power plants is very various, like pressurized water reactor, or maybe some of them in the future molten salt reactors, or from the high temperature gas cooled reactors, that the types of the waste is different. And well, this is very impressive pictures to show you the Batan Indah soil contamination activity by our colleagues here. They have collected the soil inside the drum and to carry to the nuclear facility in Serpong. The last one, I want to show you a very important things. Maybe more than 5 minutes. Sorry, not on the facility. How about waste coming from the reprocessing spent fuel? While the Indonesian government say our policy is open cycle policy. Open cycle policy means the waste generated by nuclear reactors directly goes and defined as the radioactive waste. We have, it is possible for us to reprocess the spent fuel. in the future. And it is possible to conduct research and development on the high-level waste coming from the reprocessing plant. If we declare it to the agency, to the IAEA, so it is okay, even though we have several duty to explain to the IAEA what we are doing that not violated the non-proliferation treaty. And I expect in the future we should do the reprocessing activities, although not only by ourselves, Indonesia, but the consortium with other countries, for example. So it is possible that we have to conduct the research on the high-level waste coming from the reprocessing plant. In closing, first point, radioactive waste management activities are currently only temporary and require a more integrated solution toward a safe and secure end, including the disposal. And don't forget the principle of the radioactive waste management. Radioactive waste must be managed in such a way as to avoid imposing an undue burden on future generations. Thank you very much, and I'm waiting for the comments or questions from the audience. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much, Prof. Jarod, for giving us a very informative and important presentation. I think, as I said before, that this presentation is very, very important for us, young generation and newcomer researcher in this field. Especially, it is important to put our research in the context of Indonesia. So hopefully our research will be more beneficial for our country. Thank you again, Prof. Jarod. But because of time limitation, I'd like to move on to the next presenter. I think Professor Nakashima has been joining with us now. Good afternoon, Professor Nakashima.
Good afternoon. Can you hear me?
Thank you. Yes, very clear. Yeah, thank you so much for taking time to joining with us, Professor Nakashima. So in this event, Professor Nakashima is going to give a lecture about chemistry of lanthanide and actinide, basic understanding for high-level radioactive liquid waste using solvent extraction. I think this topic is very important. As mentioned before, it's not only for waste management or waste treatment, but also for other purposes. This is just for your introduction. I think if we talk or research about uranium, thorium, or its fission product from nuclear power plant or from accelerator, we will find so many radionuclides that some of them belongs to actinide and lanthanide group, or we call it block F elements. So the understanding of their behavior, especially the chemical behavior, is very important in conducting this kind of research. So this is more or less the topic that will be discussed during Professor Nakashima lecture. But as usual, before we start the lecture, I'm going to read Professor Nakashima curriculum vitae. His name is Satoru Nakashima. He graduated from Tokyo Metropolitan University. He has some working experience. He conducted postdoctoral research at RIKEN. As you know, RIKEN is one of very prestigious research institute in Japan. After that, he conducted research fellowship at overseas institution, which is in Odense University in Denmark, before he became research associate in Department of Chemistry, and he became associate professor in 5 at Radioactive Center, Hiroshima University, and finally become a professor at Natural Science Center for Basic Research and Development, and also at Department of Chemistry, Graduate School of Science and Engineering. Maybe as you can see in his online profile, he published more than 100 publications in reputable journals. Some of them are about the separation of actinide and lanthanide using solvent extraction. He also very active in scientific community in Japan. I think, if I'm not mistaken, Professor Nakashima, he is served as president of Radiation Safety Management Society of Japan. So to make it short, I kindly invite Professor Nakashima for giving a lecture for about 40 minutes. Professor Nakashima, the time and screen are yours.
Okay. Thank you, Dr. Basky, for your kind introduction. So I would have talk chemistry of lanthanoids and actinoids. So my talk is a little bit basic chemistry. So basic understanding for selective separation of high-level radioactive liquid waste using solvent extraction. So maybe you know this is periodic table. So lanthanoids, these are lanthanoids. Lanthanoid elements have 15 elements. So these sit on this region. Also, these are actinoid elements. Actinoid elements also have 15 elements. So these are sits in this position. So I would like to explain how they are similar to each other and also how they are different from the point of chemistry. So if we know this, so we can understand how these elements can be separated. So this shows energy level of orbitals. For example, this is lanthanum element. So lanthanum element has 57 electrons. So these electrons are put from 1s orbitals to this 4f orbitals. So this electron distribution is can be written like this. So xenon plus 6s2 and 4f1. And so this 6s2 and so 4f electron can be removed. So this becomes lanthanum 3 plus cation. So the electron distribution is the same with xenon. So this shows the oxidation state of lanthanoid cations. So usually lanthanoid cation has 3 plus charge. So in this case, lanthanum has the same electron distribution of xenon. Also in the case of cerium, so xenon plus 4f1. Also by increasing the atomic number, so F electron increases step by step like this. So in the case of cerium, so cerium 3 plus has xenon 4f1, but this electron is transferred to other place. So this becomes cerium 4 plus because F0 or F7, F14 distribution are chemically stable. So cerium tend to 4 plus charge with 3 plus charge. And if we look at europium, so europium has this electron configuration. So xenon plus 4, so xenon plus 4f6 electrons. So in this case, if this europium captures electrons, so this becomes 4f7. So this is a half closed state. So this becomes europium 2 plus. So usually lanthanoid ions has 3 plus charge. And so cerium has 4 plus charge, and so europium has 2 plus charge. So shielding of F orbital again. So you can see, so this is an example of neodymium 3 plus cation. So you can see 3 4f electrons. So this cation, so the chemistry of this cation has a character like this. So to know the character of chemistry, effective number charge is very important. So effective number of charge is calculated like this. Z is this nuclear charge minus S. S is shielding constant. Shielding. So this we usually consider this electrons, but other electrons shields this nuclear charge. So this effective nuclear charge determine the chemical character of this neodymium 3 plus.
Excuse me, Prof. Nakashima.
Yes.
Could you increase your volume a little bit? Increase the volume of your Zoom. little bit. Yeah.
Can't you?
Yeah. Yes. Yeah. No. No. It's better.
Oh,
I think. Yeah.
noise.
Better sensei. Yeah. Thank you.
It's okay.
It's okay.
Okay, sorry. So by this also we consider shielding efficiency. So shielding efficiency is superior in s orbital, but f orbital has bad shielding efficiency. So by this shielding efficiency, this effective nuclear charge increases when atomic number increases. So this shows trivalent ionic radius lanthanized. So ionic radius decreases with increasing atomic number. So this is lanthanide contraction. And also, so in this case, ionic radius large. And so in this lithium, so ionic radius is small. So coordination number also changes. And also, complex formation constant also increases with increasing atomic number because the distance between positive charge and also minus charge of ligands approaches in the case of lithium. So complex formation constant also increases. So by using such change, so it is possible to separate each lanthanoid cation. So this shows ion exchange column chromatographies. If you use ion exchange resins, so and so if you put lanthanide ions, so you can see the volume element and so concentration. So at first, more smaller lithium will be eluted first, and then ethyl beam will be eluted second. So at the last, so European will be eluted. So by comparing such complex formation energy, so we can separate by using ion exchange column chromatography. Can you hear me? Okay. So I will show solvent extraction. So we can define distribution coefficient. So lanthanide cations in water phase forms complex with organic ligands. So organic ligands has no charge. So it will be moved from water phase to organic phase. So this is solvent extraction. Distribution coefficient is defined like this. So concentration of organic phase divided by concentration of water phase. So as I talked, ionic radius decreases depending on atomic number. So it is expected like the distribution coefficient increases smoothly like this, as you can see, this red dashed lines. But in that case, sometimes there is not smooth curve will be obtained like this thing. To understand this, I would have to explain such not smooth case. So to explain that, I would have shown natural abundance of the elements of, for the new universe. You can see there is up and down. So in the case of even number of atomic number, there are much natural abundance. For example, iron has 26 atomic number. So this nucleus becomes stable, and so natural abundance increases. But on the other hand, in the case of cobalt, this has 27 atomic number. So this has odd number of atomic number. In this case, it becomes unstable. So natural abundance decreases. So there is such even odd characters. So we focus this even odd character to lanthanoid elements, and also scandium and yttrium also. So you can see lanthan, praseodymium, europium, and so on. So these are 57, 59 odd number atomic number. So these natural abundance not so much. But in the case of cerium, neodymium, or samarium, so these have even number of atomic number. So this nucleus becomes stable. So natural abundance increases. So there is such even odd character in the natural abundance. So next I would like to talk standardization. So these show even odd characters, but natural abundance of the sample is divided by the natural abundance of standard. So it becomes smooth. So we call this, can you hear me? So this is standardization. But so in this case, European anomaly is observed. So this shows layers element abundance. So layers element abundance is in order of atomic number after standardization. The information about ionic radius is obtained corresponding to whether it is growing pattern or not. So yttrium 3+ has the same ionic radius of holmium 3+. So although layers elements usually become trivalent, so cesium can be tetravalent, and so europium can be divalent, as I explained. So their balance is influenced by the reductive or oxidative atmosphere. So this shows some typical layers element abundance. So you can see smooth curves, but you can see European anomaly. So this is due to oxidative or reductive situation when these rocks were formed. So also you can see this in this case natural product. I'm sorry. So you can see not so smooth curve. So you can see. So gadolinium is the center of lanthanum ions, lanthanum atoms. So the curve is different before gadolinium, and so after gadolinium. So we call this gadolinium break. And so you can see these four groups. We call this tetrad effect in natural product. So I would like to explain such gadolinium break and so tetrad effect. So we put four electrons in this region, in this 4f orbitals from lanthanum, cesium to lutetium. So electron number increases by 1. So in the case of from lanthanum to gadolinium, so total electron spin increases. On the other hand, from gadolinium to lutetium, so total electron spin decreases. So this is the origin of gadolinium break. Also, to understand tetrad effect, we have to consider magnetic quantum number. So f orbital can be separated by this magnetic quantum number. So 3, 2, 1, 0, -1, -2, -3. These are magnetic quantum number. So by putting electrons here, so in this yellow region, total this magnetic quantum number increases. On the other hand, from here to here, total magnetic quantum number decreases. And also from here to here, total magnetic number increases again, and from here to here, total magnetic number decreases. So this is the origin of tetrad effect. So we have to consider such very sensitive change to understand the change of chemical character in lanthanoid elements. And so I would like to move the chemistry of actinide element. So they exhibit similar properties with the lanthanoid, but for thorium, protactinium, uranium, and neptunium, so there's a difference. However, electronic cloud of 5f orbital is large compared with that of 4f orbital, and the energy of the orbital of 6d, 7s, 7p orbital is comparable. Then compound having a wide range of oxidation number is produced by the orbital hybridization. So in the case of lanthanide, so pure ionic bond. On the other hand, in the case of actinide, this is the ionic bond, including covalent bond. So if it is trivalent ion, there's the same tendency as the lanthanide contractions. So this shows the same figure. This shows trivalent ionic radius of actinide. So you can see these are the ionic radius of actinide elements. So ionic radius decreases with increasing atomic number. So we call this actinide contraction. So this is due to effective atomic charge. Also, the difference between actinide and also lanthanide is only 5 picometer. Also, coordination number also maybe changes. Also, complex formation constant increases with increasing atomic number. So this is the same with the result of lanthanoids. So next, I will show ion exchange chromatography. So we put here actinide ions. So smaller actinide ions forms stable complex with ligands. So smaller one. So Mendeleev.
Sorry, I'm so sorry to all audience. Please take care you have to unmute your mic.
So Mendeleev is first eluted first, and so Fermi is the second. So it is possible to separate by using ion exchange chromatography. So next shows oxidation states of actinide elements. So you can see from americium to lawrencium. So main oxidation state is 3+. But on the other hand, in the case from the sodium to plutonium, so oxidation state is more than 3+. So in this region, so chemical behavior is different from lanthanoids. So you can see this direction shows oxidation state, and this direction shows how such oxidation state becomes stable. So in the case of sodium, 4+ charge, so 4+ oxidation state is stable. And so if we look at uranium, so from 3, 4, 5 to 6, they are stable. So the chemical behavior of these sodium to plutonium are a little different from lanthanoid. But from americium to lawrencium, chemical behavior is similar to lanthanoid. So I talked the chemistry of lanthanoids, and so I talked chemistry of actinide. So I would have moved chemical separation of lanthanoids and also actinides. So we have spent new fuels. So if we keep spent fuels, so we have to keep spent fuel about 100,000 years. It's very long period. So if we reprocess, so we take uranium, plutonium, so it becomes high-level waste. So in the case of high-level waste, so we have to keep several thousand years. And so if separates lanthanoids and minor actinoids, and so if we transfer minor actinoids by irradiating neutrons to form shorter having shorter half-lives elements. So in that case, we keep maybe several hundred years. So please imagine. So we can control such waste for 100 or several hundred years, but we cannot imagine so the keeping of several thousand years. So in this case, partitioning and transmutation becomes very important. So this is a technique to separate radioactive nuclides involved in high-level radioactive waste, depending on the half-life and purpose of use, and to convert them to short-lived nucleus or non-radioactive nucleus. So to do partitioning and transmutation, so chemical separation becomes important. So this shows chemical separation of lanthanoids and actinoids. So lanthanoids cations, lanthanoid cations or actinoid cations are dissolved in water phase. So if we add organic ligand, so this makes this forms complex. This complex becomes neutrals. So this neutrals complex can be moved from water phase to organic phase. So this complex can be separated. So we already define this constant. So this is calculated like this. This metal concentration in organic phase divided by the concentration of water phase. So you can see if you use S donor, so and also we define separation factor. Separation factor is defined like this: D americium divided by D europiums. So in this case, if you use sulfur containing ligand, so separation factor becomes large. And so if you use this nitrogen containing ligands, so the separation factor becomes 100. On the other hand, if you use oxygen containing ligands, so separation factor becomes lower than 1. So if the separation factor larger than 1, so americium will be selectively separated. On the other hand, if the separation factor is smaller than 1, so europium will be separated. So to understand such phenomena, we performed DFT calculation. So in that case, we have to know the free energy difference from metals surrounded by water molecules to the metals surrounded by ligands. So the delta G, we calculate delta G's. So to perform DFT calculation, we have to know structure optimization. So if we know structure, so if we input such data to this DFT method, so we can get output. But is the result okay? This is a very big problem. Also, to calculate this DFT calculation, so we use several types of functionals. So is functional is adequate or not? This is also important. And also, lanthanoids, also actinoids, has a big nucleus. In that case, relativist effect becomes important. For example, in heavy atoms, the interaction between electrons and nucleus is enhanced significantly because the nuclear positive charge is very large. So if we consider S electrons and also P electrons, so these are approaches to nucleus. So this is a direct relativist effect. On the other hand, in the case of D electrons and also F electrons, so in this case, S electrons, P electrons shields very effectively. So D electrons and also F electrons, so becomes far from nucleus. So this is indirect relativistic effect. So we have to such a relativistic effect. So to know, so that the calculation result is okay or not. So also we have to consider relativistic effect. So we have to compare the results obtained from DFT calculation with the experimental results. To compare them, we use Mossbauer effect. So Mossbauer effect is a resonance of gamma rays. So, but this gamma ray energies changes depending on chemical state. So this is a shift of gamma ray resonance. So gamma ray resonance shifted by a chemical effect. So this shows this. We call this isomer shift. Isomer shift is proportional to the density, electron density at the nuclear position. So we have such linear relations. So we compare the linearity. So we change the functions. For example, BP86, B3 LYP, also B2 PLYP. So the judge is the linearity. So if we use, you can see the linearity becomes better. So this shows B2 PLYP function is better to calculate the energy of lanthanoids. Also, we performed benchmark study of actinides. So in this case also we use Mossbauer effect. So in this case, the Mossbauer effect of Neptunium-237. In this case also, experimental isomer shift is proportional to the density at the nucleus position. This density can be calculated from Dft calculation. If the linearity is good, so the functional and also the results becomes good. So so it is better to compare the linearity. In this case also, B2 PLYP functional is the best functional. So after such benchmark study, we performed computational studies. So in the case of all donor, so metals react with this oxygen donor, so which makes this complex. Also, in the case of S donor, we use this ligand, and in the case of N donor, we use this ligand. So after the reaction, we obtain these complexes. So after structure optimization, we performed Dft calculation. So this is the results. So you can see this is a experimental results. So this is a this value is a delta G. So this means the delta G, the difference between delta G of European minus delta G of American. So delta G we consider. So if this value is positive, so in this case, American selectivity. On the other hand, in this case, minus value. So in this case, Europeans, this shows European selectivities. Also, we performed the Dft calculation of the complexes. So in the if we use B2 PLP, so the results are relatively good, but not so perfect. In this is the result of gas phase. Also, we considered water phase results by using Cosmo program. So in this case, we consider hydration. That is yes. So these are the results, and so the results obtained using B2 PLP becomes better. So we reproduce such American or European selectivities. Also, by using the results, we check the contribution of orbitals, d electrons or f orbitals, or we consider such contribution of d orbitals or f orbitals. So in the case of S donor and so N donor, the interaction between American and so ligands, the interaction is bonding character. On the other hand, in the case of European, so the interaction is non-bonding. So this is the reason why if we use S donor or N donor, this shows American selectivity. On the other hand, if we use all donors, so in the case of European complex, so this shows bonding character between European and also ligands. On the other hand, in the case of American and ligands, so in this case, anti-bonding. So such difference becomes a cause of European selectivities. So by using such Dft calculation. So we reproduced the experimental results. So maybe this is a last PowerPoint. So this is a summary. So I talked chemistry of lantanoid changes systematically depending on atomic number. Also, we found Cerium anomaly and so European anomalies. So one lanthanol element can be separated from other lanthanol series by using systematic chemical changes. Also, I thought chemistry of lanthanol. So chemistry of lanthanol changes systematically depending on atomic number. And so sodium to plutonium element tend to have higher oxidation state than 3+. So one actinide element can be separated from other actinide series by using such chemical difference in actinide series. Also, electronic cloud of 5f orbital is larger than that of 4f orbitals. So by using such difference, actinide can be separated from lantanoid. So that's all. Thank you for kind attention.
Thank you so much, Prof. Nakashima, for I think this is very important basic information for us. So because of time limitation, now we are going to move on to the commentary session. But based on the, there is a request from Pak Saiful, the head of our research center. So, Prof. Nakashima, maybe I will little bit explain what you have taught in this presentation in Bahasa, just to elaborate a little bit about your presentation. So, Bapak-bapak, Ibu-ibu sekalian, baru saja Prof. Nakashima telah memaparkan kepada kita semua tentang dasar-dasar kimia lanthanide dan actinide yang tadi sudah dijelaskan bahwa ada persamaan dan ada perbedaannya. Dari persamaan dan perbedaannya itu sangat penting untuk menjadikan dasar bagi kita melakukan riset, terutama untuk riset separasi dari actinide dan lanthanide. Sebagaimana tadi sudah dijelaskan oleh Prof. Nakashima bahwa seandainya kita melakukan riset terkait dengan pengelolaan spent fuel, kalau kita tidak melakukan reprocessing, maka akan membutuhkan waktu ribuan tahun untuk menyimpannya. Tapi ketika kita melakukan separasi, misalnya uranium dan plutonium, itu menjadi decrease menjadi hanya ribuan tahun. Kemudian jika kita mengambil lanthanide dan minor actinide, itu kita hanya cukup menyimpan sekitar 100 tahunan. Jadi itu sangat penting. Jadi yang dijelaskan oleh Prof. Nakashima terkait dengan persamaan dan perbedaan sifat kimia tadi sangat penting digunakan untuk penelitian separasi actinide dan lanthanide. Mungkin seperti itu. Nanti Bapak Ibu bisa bertanya lebih lanjut ke beliau, bisa dalam bahasa Indonesia atau bahasa Inggris. Sorry, Prof. Nakashima, I'm explaining your presentation again little bit to elaborate to our audience in Bahasa. Thank you so much. So in order to continue our event, time limitation, as I mentioned before, now we have two commentators in this event. So I would like to invite our commentators. First, I would like to invite Dr. Adi Raga for giving comment or sharing. You also not only can give comment about the lecture, but also you can share the research or activity in your university related to radioactive waste management related research topic. So you can share also about that. Your time is about 10 minutes. Please, Dr. Raga.
Okay, thank you, Dr. Basuki. Ladies and gentlemen, can you hear my voice?
Yes, very clear, Dr.
Okay, thank you very much, Dr. Basuki. Good afternoon, everyone. First of all, thank you very much for a really interesting presentation from Professor Jarod and Professor Nakashima. I have several points, and maybe I summarize a little bit both of the presentation. First of all, from Professor Jarod, I'm really interested with the problem that you mentioned in the beginning of your presentation about the question of now that Batam is integrated to BRIN, then who will be the body of radioactive waste management? If I use the term correctly, is it the body of waste management, or
I
is
think
there any?
we call it Badan Pelaksana or implementation body.
Oh, implementation body. Yeah, sorry. Yeah, I'm really interested with that point that you mentioned in your presentation, because I don't know. I wonder that. I wonder if something as important as radioactive waste management is managed by a body that is very large as BRIN, very large and very general. I think I wonder if it is ideal or not, because I think the responsible or the implementation body need to be in the right size, and it has to be specific, I think. I mean, so the top management also understand the importance of radioactive waste management, so that the decision can be speed up or can be as soon as possible if there is a problem in the field. So can I also have a question, Dr. Basuki, or it's just I only comment?
Of course. Of course, you can have a question.
Okay.
Okay. Yeah. So in Professor Jarod' opinion, what is the best organizational model to for this problem, or for this radioactive waste management handling model, organizational model? What is the best way to do it, Professor Jarod? Maybe that's my question. Yeah.
Pak Triyono, can I answer or later on?
I think it's better to wait the second commentator to give comment.
Okay.
To keep our time, manage our time effectively. Okay.
Thank you.
Yeah, is enough.
And maybe if I may share my as you said, yeah, I can also share my my research experience.
Yes,
Actually, yeah, actually, I just finished supervise a master student from Bapeten this semester. During the examination, also assessed by Pak Hendra from from BRIN, and his research, or Mr. Hermawan research, was about the recycle of tin slag as a mixture for mortar, and as a result, and the result was the mixture or the mortar has a good quality. However, after we model the risk or model the effective dose for industrial and for settlement usage, the dose is still relatively larger than 1 millisievert. And I think I agree with the future of the research that is Professor Jarod mentioned in his presentation, that we do really need to study about the tin slag or the norm or tin norm recycle, so that because it's abundance amount, and we need to know what is the best ideal to manage that, to reduce the amount, to recycle it, and how to properly dispose that kind of waste. And if I may continue to Professor Nakashima, well, to be honest, I don't have a strong chemical background. So I just maybe have a question, but it's related to the slag or the T norm or T norm treatment technology. I wonder if such kind of lanthionide or anthracite, as you said, it is used for fuel or spent fuel waste. However, will it be too expensive if we use it for lower radioactive waste, but in the large amount, or for example, like mining slag, because the amount of radioactive is not really low. I think it's in medium. The abundance is very large, But will it be too expensive if we use lanthionide and antonite for that application? Maybe that's all from me, Dr. Basuki. Thank you.
Thank you so much, Dr. Adiraga. Prof. Jarod, Prof. Nasim, I think I changed my mind because of there are a lot of questions. I'm afraid that we lost the question, so it's better to answer directly. Please,
Okay.
at first, Prof. Jarod.
Okay, thank you very much, Pak Adiraga. This is very interesting questions about what kind of organizations that can manage the radioactive waste in Indonesia. I think BRIN now is in the process of evolution. I think the current organizations probably in the near future will change. Well, anyway, every day we have to face many changes with the policy and strategy. But when you ask me about the proper organizations, if the BRIN only focusing on the research, so the government should have another organization that dedicating on the nuclear utilization, nuclear and services. This is stated in the Act of Number 10, 1997. So the implementing body not only doing the research, but also to give the services, including the radioactive waste management, also the promotion. Well, BRIN is very big organization. Maybe they promote everything inside what is our capability and other, including the space, for example, or maybe the virus and other things, vaccine and other things. Nuclear is just small part of that. That's why I always propose if BRIN, if Indonesia want to promote nuclear more actively, it is better to have a new organization like Batan in the previous era that not doing the research, maybe research inside the BRIN, but doing the promotion services and also, well, because we are dealing with the radioactive materials that maybe is risky for the public. We also protect the people and the environment. So this is my opinion. Maybe some people will not agree with my statement, but anyway, we have for me, nuclear is very unique business, when I call it business, that not only to utilize the radioactive materials, but also to protect everyone. It is very different with the other technologies. This is my opinion. Thank you.
Thank you. Thank you so much, Prof. Jarod, for the answer. For the second question, but I don't really catch your question actually at the time. But in my understanding, your question is about the separation or uptake of the thorium or uranium from the slag, I think, yeah. I think
And it's like actually, Dr. Basuki, because
any slag, not only, yeah. Maybe the question is how effective the method, I think, yeah, to separate the thorium and uranium from the. In Indonesia, we have so many mining, and the mining process produce the waste, and this waste we call it slag. In this slag contain many elements, including rare earth element, thorium, uranium, and so on. So one of our research aims is to separate the uranium and thorium from this slag. And do you think that the method that you have explained can be used effectively to separate uranium and thorium? And maybe this is just addition from me. Based on your explanation, uranium and thorium has a different character than other actinide element. It has multivalent or oxidation state. Maybe can be tetravalent or pentavalent and so on. So in my opinion, it's little bit easier to be separated. Am I right?
I think so. So balance state is different. So it's relatively easy to separate thorium or uranium from other actinoids. I think so. But I think Baski-san's understanding is correct. I think so. It's okay, Mike.
Yeah, yes. What do you think, Dr. Radyo? Is it enough?
And will it be too expensive if we implement it to manage our mining slack with this technology? And that's my last question. Okay.
Okay. Is it expensive or not, Prof. Sagwa? Maybe we haven't reached that stage, yeah, Sensei.
We haven't reached this.
Yeah, we
Okay,
just did the best research. This is also my research plan that I proposed to BRIN through the RIM proposal. So I also submitted this kind of research, basic science research. Maybe we can collaborate.
Okay, I'm looking forward to hear the result, Dr. Basuki, Professor. Okay,
Yeah.
thank you.
Thank you. Let's move on to the next commentators. So I will invite Bapak Susetya to give your comments, please.
Okay, thank you, Pak Triyono. I'm not so confident to give some commentary because I'm the junior of Pak Jarod, not only in
No, you are expert also. I think.
Not only in Universitas Gadjah Mada, but also in the senior high school. But I have to make some comment. First, I agree with Pak Jarod about that many people always ask about how to handle the radioactive waste in Indonesia, and we realize that we always say that showing our competency in handling the radioactive waste is one of the key success factor in utilization of nuclear technology in Indonesia. So we put it in our mind, and we make some research related to the radioactive waste management. The second one, Pak Jarod said that many people confuse between handling radioactive waste with garbage management. So I think one of the what should we do is to educate and train many people in that we can that they understand how we handle the radioactive waste. I mean that the education is not only in the role of university, but all of stakeholder in radioactive waste management, including BRIN in this case. The third, I agree to Pak Setiawan that 3R, reuse, reduce, and reprocessing approach is necessary to implement in the radioactive waste management to avoid the limitation of BRIN facilities. It's the third note for me, and it's the fourth. It's the first time for me to hear that the tariff policy will have an impact to safety and security. But I believe that it is not a single reason to make some low tariff in radioactive waste handling in BRIN. I think that's all of my commentary for Pak Jarod, and I think Pak Jarod gotong royong is a must to to show that we could manage properly the radioactive waste in Indonesia. And not commentary, but I have a question to Nakashima Sensei, but maybe not related to your research, but I need your opinion. When I visit GAE in Tokaimura, I saw that some private company also have also participate in some activities, including radioactive waste management. I just wonder how Japan develop nuclear security in their facilities when some private company also could come and actively doing some activities in the facility. Thank you.
Thank you so much, Pak Susetio, for important comments and also question. Okay, I think it's nice if Professor Nakashima also could share the experience of Japan, because you are the president of Japanese Society for Radiation Safety Management. So you also could share the management of radioactive waste in Japan. I think you also could little bit share to us. But at first, I will give a chance to Prof. Jarod to answer the question.
Okay, thank you very much, Pak Susetio, because Pak Susetio in the Gajah Mada University, I think your lectures topics including radioactive waste and also the nuclear security, isn't it? So I agree. First, when we have a gotong royong or mutual agreement or joint works on this radioactive waste. So the center of the Pak Saiful Center right now, I think we have an agreement with the Gajah Mada University on joint works of several topics. Yes, of course, when we talk about radioactive waste management, we have also to believe the 3R, as the Professor Budistiawan said: reuse, recycle, reduce, reuse, and recycle. What we have done right now in BRIN is reduce and reuse, but recycle, it needs some additional facility like hot cells. Maybe we have to activate our hot cells, and also how to conduct several research study on the recovery of the disused sources. This is very challenging, of course, but very good when we talk about economy of this kind of disused sources. And this activity of recycle or reuse is also reduce the waste inside the interim storage. This is really, I agree with you 100%. The second thing about the tariff, well, I always remember 2 decades ago, 2 decades ago, yes, I think I was very young, more than 2 decades ago, when we set up the tariff, the calculation. I think Pak Sumar Bagiono in here also, Pak Suryanto, we calculate everything. Then, for example, for radium needles, very high, very high. Well, I don't remember the exact tariff of that, but there was complaint from the chairman of BAPTEN. Look, if this tariff is expensive, then everyone will dump their radioactive waste everywhere. Post a release for the safety and security. His statement, Dr. Ridwan at that time. That's why we reduced that. We didn't calculate the long-term storage, disposal calculation or considerations. That's why, right at the moment, the time is very.
But the Batan Indah case showed another reason.
Batan Indah case is very source, and I learned from the Batan Indah case. It's because the process business from the waste generator to Serpong, there is I think a hole that another entity can use it. Some people maybe they don't want to communicate directly with us. Then some people, some entity just promote, look, I will take care your radioactive source, and I will communicate with Bapeten to get the permission, and then the accident happened.
Okay.
And so this is the lesson from the Bapeten,
Yeah.
the Batan in that case.
Yes, yeah.
Yeah. Thank you, Michael. This is Michael.
Thank you so much, Prof. Jarod, for a nice answer. Prof. Nagashima, just a little bit, could you share with us about the radioactive waste management in Japan? Just a little bit. Thank you so much.
Okay, I'm not sure I understand the question. I'm not so sure, but so there is a big facility in Tokamura, so that is correct. And also, in Japan, we have small radar centers in each university. So we control we management the facilities, and also we have a chance to educate radars of isotopes and so radiation to the students. So is this correct answer or not? I'm not so sure.
Maybe I expect you to explain to us the general radioactive waste management in Japan, like how you deal with liquid waste or how you deal with solid waste, especially in our laboratory, for example, in our radioisotope center. Maybe you could explain a bit as well. And about the tariff, is it expensive or not, for example?
Actually, maybe Japan Radioisotope Association. We will say. I'm sorry. I'm sorry. It's not easy to explain in English, but we keep radar materials, radioactive waste in our facilities. Also, Japan Radar Association takes our waste once per year. I'm not so sure my question is okay or not. I'm sorry.
I think it's okay. I think it's okay. I remember that every year we send the waste, our radioactive waste, to the Japan Radioisotope Association, I think, and they will manage the waste. But we don't know exactly what happened in Japan Radioisotope Association. Okay, maybe for the last.
Adriano, maybe
yes. Okay, you
okay. I think now we have 3 issues that we have to face in the future. First is how to deal with the new radioactive waste from that Jarod mentioned before, from our old reactor and maybe our first nuclear power plant, maybe new generation of nuclear power plant, and the new radiological facilities in the first. The second is how to gain public trust, mean how to show our achievement, not only BRIN, but also the university also, in the handling of radioactive waste that could increase their trust to us in dealing in utilization of nuclear technology in Indonesia. And the last one is how to improve our technology independence that is related to improving the competencies of human resources which deal in the waste, improving our facilities for handling and research, that maybe a new kind of waste will come if we utilize new generation of nuclear power plant. Then we should also improving the local material content. I know that BRIN and also in Gadjah Mada University have some research related to the local material for absorbing the radioisotope. And the last is transferring the invention to be the product of related industry. That it's related to my question to Nakashima Sensei. that I saw some private company in Japan also participate in dealing with the nuclear technology. Maybe the first obstacle is our regulation in Indonesia, especially related to the radioactive waste management. In our decree number 10, it declared that nuclear radioactive waste management have to manage by Patan, or now become a BRIN. I think it's my last comment for the audience. Thank you.
Thank you so much, Pak Susityo, for the very important comments. I do agree with you, especially about improving the human resource, the facility, and also maybe regulation, ya, Pak Susityo, ya, in order to deal with the radioactive waste. And maybe more important is to involve maybe more stakeholder, I think, yeah, Susityo, to be involved in this effort. Maybe for the last chance in this commentary session, Prof. Jarod or Prof. Nakashima, do you have, for example, Prof. Jarod, do you have comment for Prof. Nakashima presentation?
Okay, thank you very much.
Yeah.
Oh, well, Professor Nakashima, I remember when I was in master and doctor in the University of Tokyo, my study was on the transuranium separation in the partitioning process. So maybe, but I already forgot that kind of activities a long time ago. My master was on the separation of americium using the solvent extraction, DIDPA, the extractant developed by Jairi at the time. And then my doctorate is also the solvent extraction process on the separation of pentavalent neptunium using CMPO. I forgot the longer name of the CMPO. But my questions to you is that the partitioning activity still exists in Japan or not? I think at that time we were very active on the partitioning or including the transmutation and other things. How is right now in Japan? This is my question to Nakashima-sensei.
Thank you, Prof. Jarod. Please, Prof. Nakashima.
It's better to do partitioning, but so in Japan not so processed such partitioning. So maybe so it's future plan. So
okay,
not yet. Yeah.
Okay. Thank you.
Okay, thank you so much, Prof. Jarod, Prof. Nakashima, and all commentators for very nice and active discussion. So because of time limitation, we have to move on to the next session. So the next session, I'm going to open the question and answer session for all audience. So all audience, if you have a question or comment, please use your in your Zoom. And please also unmute your mic and also switch on your camera. Is there any question from the audience? I think, Pak, I forget. There is a question in the chat box from Bapak Winter Dewantara. Could you ask the question directly, Pak Winter? Are you still in our meeting or not? Okay, if not,
I think it's clear from chat box.
yes. to make it more, interactive.
Okay.
Please, Pak Winter.
Mr. Jarod. It's a cementing method, the only method to processing waste in radioactive waste management installation now, but because I know other method is available theoretically in the world. If if why choose the method, because what the advantage or disadvantage the method compare than other methods? That's my question.
Thank you so much, Pak Winter. If there are other questions, I would like to invite 2 more participants. Anyone? And you also can ask question in Bahasa Indonesia, of course. If not, Prof. Jarod, please.
Okay, thank you. I think Pak Winter asked me about the why BRIN or Badan choose cement for the solidification rather than the other technology. What is the advantage and disadvantage of that cement? Yes, cement or concrete is an inexpensive, cheap, quick and durable way for the solidification. However, there are advantages and disadvantages associated with this cement or concrete. For example, while concrete becomes stronger and more durable with time, it is susceptible to water. And for the countries that suffering with cold, like winter, that water can seep it in Bahasa Indonesia is meresap into cracks and cause damage to the concrete. But anyway, every technology have their own advantage and disadvantage. We have other options like bitumen. Bitumen, in other words, it's called asphalt. In us, maybe is not cheap, more expensive than concrete. And concrete is everywhere in our neighboring location. That's why we choose concrete rather than bitumen. And there are a lot of study comparing the cement and bitumen. And for us, well, for the country with high temperature, we choose the cement or concrete. And there is another solidification technology using the glass vitrification. But this is very durable, very good in the physical characterization, but very expensive. This glass or vitrification is dedicated for the high-level waste. If we choose the reprocessing policy, and we have to manage the high-level waste coming from the reprocessing facilities. This is my answer. Thank you.
Thank you so much, Prof. Jarod. Ladies and gentlemen, I actually found 2 more questions on the chat box, but because of time limitation, I'd like to read the question. The question is from Professor Budi Setiawan. His question is, research on the extraction of actinide and lanthionide is very important for the countries with closed cycle waste management policies. But how about for the countries with open cycle waste management policies? I think this question may be directed to Prof. Jarod, I think, because of about policy. Yeah.
Well, for the research, we have to, not limited on the open or closed fuel cycle. Our research on the lanthionide correlated with the rare earths, for example. Well, the use of rare earth is very important for the industry, not necessarily for the radioactive waste management. For the future, I expect with the demand of the uranium become high, because every country wants to use the nuclear power plant, while the supply of uranium is very limited also. So the reprocessing facility is, we cannot to avoid, although we have to declare ourselves on the ratification on the non-proliferation treaty. That's why the separation of the fission product from the transuranium, from the lanthionide is very important also. Although if we choose whether this is a short-term tema or topics or not, maybe it's not short-term topics. But for the from the point of rare earths utilization, this is very important. Thank you.
Thank you so much, Prof. Jarod. Maybe this is the last question, but it's not. I think it's not easy question. From Mr. Kowalski, I don't know from where he is. Can we synergistically combine physical and chemical technologies to tackle problems of plastic waste and nuclear waste together? I think it's not easy question. Anyone could answer this question or not? Maybe.
Well, I think everywhere in the world, when we are doing the research, this is the combination of the physical and chemical technology. We cannot avoid. We just to use the chemistry only. No, we also use the physical technology also. It is very difficult to do the separate that kind of.
Thank you so much.
But anyway, when we talk about the plastic, it's very because this is not the of my specialty. I cannot answer that.
Yeah. Okay, thank you so much, Prof. Jarod. I would like to invite more questions if there are questions or comment. If not, Prof. Jarod, I have one question for you.
Please.
And maybe one question for Prof. Nakashima. Prof. Jarod, I think this kind of event, we talk about webinar event or seminar event, one of the aims is to attract researchers to be involved in this research in this field. So by involving more researchers to conduct research in this field, so we can, we can get we can get more research. And develop more technologies and capacities, especially in Indonesia. What do you think? Do you have idea how to attract more researchers to join with us in this research field?
Okay, this question is correlated with Pak Susatyo comments on how to increase our community, nuclear community. That's why it is very important to have a philosophy of gotong royong or mutual cooperation. So we have to promote to many universities. This is also the opportunity of BRIN. BRIN always encourage us to cooperate with other entities in Indonesia, even not in Indonesia, even outside the Indonesia. I will explain why we always fail unsuccessful to implement the nuclear energy program in Indonesia, because only Batam and Bapeten doing the nuclear activities. We have a small number of community in Indonesia, nuclear community, unlike Japan. Japan have many communities in industry, in universities, and the JAA. That's why we conduct the webinar, HIMNI webinar every Thursday. One point we want to reach the target is to increase our network, to give the explanations, whether this is technical or general explanation. This is radioactivity, this is nuclear energy, this is radioactive waste. With that kind of methods, we expect there are a lot of people, there are a lot of universities and industries that attract and join us to conduct the research on the nuclear energy and especially on the radioactive waste management. This is my answer. Thank you, Pak.
Thank you so much, Prof. Jarod. I remember I think we had this discussion in Tokyo some years ago. I think you said to me that Batam is single player in nuclear field.
Yeah.
So we have to expand the stakeholders. Thank you so much, Prof. Jarod. And the question for Prof. Nakashima, I think based on your explanation, the ligand is very important. The developing of ligand is very important. I see that maybe sulfur donor ligand is more better separation of europium over americium, I think. So as I know that the research in this field is about the developing of the ligand. So I have a question about the research direction in this field. Do we still have like a novel idea to do research that can be published in a reputable journal and can be beneficial for our society? And the second one, maybe, do you open for collaboration, or maybe if somebody from this Zoom meeting going to learn from you, are you open for that opportunity? Thank you so much.
The chemistry of lanthanoids and also actinoids itself is interesting. For example, we don't know exactly the chemistry of heavier actinoid. For example, because they are artificial elements, we don't have much data concerning very precise chemistry of such heavier actinoid. For example, you consider Lorentz. So even the ionic ionization potential, it's not easy to measure such ionization potential. Several years ago, JAEA's person revealed ionization energies of Lorentz, for example. So such very basic knowledge was published, maybe published in Science or Nature. So I think such chemistry is very important. And also from the point of application, So I talked solvent extraction from water phase to organic phase. But if we obtain back extraction from organic phase to water phase, so by improving such techniques, so we can use ligands repeatedly, for example. So I think there's much sciences and also technologies in these fields. This is my answer. I couldn't follow your second question.
Yeah, are you open for the collaboration, or if somebody want to learn from you, are you open for that opportunities?
I hope so. It's better to collaborate. I think so. It's good.
Thank you so much, Dr. Nakashima. Maybe last question. This is from our researcher at our group, research center, from Dr. Jakar Nadetian. The question is for phosphonic and phthophosphonic acid. You hear me, Sensei?
I'm sorry.
For phosphinic and phthophosphinic acid, they have similar structure. The only difference is oxygen and sulfur atoms. But the selectivity for americium and europium is 5 order magnitude different. How could you explain this phenomenon?
The structure is similar.
Yes.
Structure is similar, but interaction between americium and also sulfur. The interaction between americium and sulfur and so americium oxygen. So such interaction between the two is different between oxygen and sulfur. Can you follow me?
I think Dr. Jaka should raise your hand and ask us directly.
Yeah. Okay.
Could you follow? Oh, yeah. Okay.
Yeah. So from your presentation, you have some ligand. I think you have 3 ligands and 2 ligands for phosphonic acid and phytophosphonic acid. They have similar structure. The only difference in the oxygen atom and sulfur atom, I think. But the selectivity coefficient is different to 5 order magnitudes, and how to explain this and whether it's applicable to only selectivity americium europium, or it's applicable to all of the actinides. And can I continue my question, or Nakashima Sensei answer first?
maybe there are. I think there are 2 points. But one is one ligand forms dimer. The other is not form dimer. So there's a such difference. And also the interaction between metals and nitrogen or sulfur or oxygen are defined.
Okay. So I have another question. So you have another ligand, different structure, but you only explain about effect of sulfur, oxygen, and nitrogen atom in the ligand, the complex between that atom to the actinide. And do you think it's only the three atom is only affecting the separation, or the other structure like alkyl group, the carbon chain, or the aromatic chain in the organic ligands affect the separation between these actinides?
So thank you for questions. Maybe we introduce, for example, electron donating group or electron withdrawing groups. So the binding constant a little bit increased or decreased. By increasing or decreasing, so separation factor a little bit affected. So in other, if we use other ligands, also we introduce halogens. So separation factors will be changed. So by designing ligands, so selectivity will be affected.
Yeah. Okay. Thank you. Can I have one last question? So you have.
Okay.
So
Maybe
you have.
the very last question in this event, Dr. Jaka.
Okay. So you explain the separation by density functional theory. I think the simulation. Can we confirm the result by the experiment in the lab, doing the same the same purpose to confirm the Dft calculation and the experiment in the lab measuring the selectivity between the organic ligands and the for the actinides?
So we have to compare the experiment results and also Dft results. We have to compare, but actually we can treat americium in our laboratory. So we compare our results with the data from papers.
Is that okay, Dr. Jaka?
Yeah.
I think it's
thank you, Rakesh Sensei.
Yes, it's very usual. The computational chemistry result should be compared with the experimental. I think it's very okay. Thank you so much, Prof. Jarod, Prof. Nakashima, all commentators, and all participants for very active question and answer session. But because of time limitation, I think we are about to close this session. In this session, I will not make any conclusion because so many information that we obtained from the presentation and discussion. But I do believe that all of you have obtained important information that I hope that will be beneficial for all of you. And to close this session, I'd like to thank to Prof. Jarod, Prof. Nakashima, all commentators for lecture, for sharing, and also for all audience for very active contribution during this session. And I would like to close this session, but before we close this session, please give a big applause for all of us. Thank you so much again for your participation. I return to Dr. Muhammad Yusuf, please.
Okay, thank you so much for Dr. Triana for leading the sessions. And also thank you so much for all distinguished the speakers, moderator, and all the participants who were active during the lecture and discussions. Now we are coming to the end sessions. However, we would like to invite our coordinator of this group, Dr. Hendra Adi Pratama, to deliver some conclusion remarks and also officially close this session today. To Dr. Hendra Adi Pratama, time and screen are yours.
Thank you very much, Mr. Yusuf. Can you hear me clearly? Oh,
yeah.
Okay.
Yes, good.
Okay, to all distinguished speaker, Prof. Nakashima and Prof. Jarod, and also our commentary from University of Indonesia, Dr. Adiraga Pratama, and also from the Gajah Mada University, Pak Susetio. I would like to thank you for doing this webinar and all of you to attending this very nice lecture from both of speaker. And I would like to comment here that I hope that this is not the end of the webinar, so we can move to the next level to maybe to make some collaboration of research or some kind of activity in the future. So and also thank you for the committee to prepare of this webinar so we can follow nicely until the end. And I, on behalf of the head of the research center of nuclear fuel cycle and radioactive waste, I would like to close this webinar by saying Alhamdulillah, Alhamdulillahirabbil alamin. And thank you very much. And time I will give it back to Mr. Muhammad Yusuf as ceremony master. Thank you very much.
Okay, thank you so much, Dr. Hendra Adi Pratama, for closing this session officially. And before we end this session, we would like to remind you again for all participants that you are now have eligibility to download the certificate and the materials through the Linktree site, which you can find on the chat box. And now we are in the end of the sessions. Thank you so much again for all of you. And don't forget to follow and attend to our next sharing sessions. See you all in the next sharing knowledge webinar session. See you and bye-bye.